All right, I think we can start. Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Manxi, who is an assistant professor at the School of Operation Research and Information Engineering at Cornell University. Something about Manxi, she earned her PhD in social and engineering systems from MIT, where she was working in the Institute for Data Systems and Society. And then prior to joining Cornell, she was a research fellow at the Simons Program on Learning and Games and a postdoctoral scholar at Berkeley. In general, research focuses on analyzing the strategic behavior of travelers and its impact of urban systems using game theory, optimization, and machine learning techniques. She also works on designing information and market mechanisms to enhance system efficiency, resiliency, and fairness. She obtained a number of fellowships, and today she's going to talk about spatiotemporal pricing for efficient autonomous carpooling markets. This is a topic which is very interesting for our group, and therefore I'm very excited to give you the stage, Manxi. Go ahead.
Yeah, thanks for the kind introduction. So before I decided topic, I briefly skimmed through the research topics that are the exciting research that are happening in the group, and I actually found some very related papers. So I'm very much looking forward to having a fruitful discussion today. So this is actually the preliminary version of this work. Was done when I was a last year PhD student at MIT. And then I took the year during my postdoc to have a more complete picture of this topic. And this work is joined with my student at Cornell, Ori, Priya, and also with two mentors for my PhD, Saurabh and Patrick from MIT. Okay, so feel free to interrupt me and ask questions in the middle. So this work is really motivated to think about what's the impact of autonomous driving technology on the future mobility platforms. No matter how advanced these technologies are, for example, there are evidence or experiments showing that they can make the traffic more smooth and they can potentially increase the road capacity to have a higher throughput of the system. However, on the other hand, it also lowers the cost of traveling. And it is unclear to me how is today's traffic network with limited capacity are going to accommodate the increasing travel demand when the travel cost as well as the mental burden of driving is significantly reduced by this autonomous driving technology. Despite its capability of increasing the throughput and keep the system safer, the fundamental problem of incentives still exists. In particular, whether or not carpooling technology is going to improve or make traffic worse very much depends on how we incentivize our travelers to share the road capacity. If we design a proper mechanism that can incentivize people to efficiently share the roads, we will see that the vehicle miles traveled will be decreased and there will be less congestion and pollution. On the other hand, if we do not regulate such incentive and just let people travel based on their self-interest, then the low cost of autonomous carpool will turn the road network into potentially even a parking lot, and there will be more pollution. So the question that we focus on this paper is how can we incentivize riders with heterogeneous preferences to take carpool trips and share road capacity efficiently? And just to have a simple thought experiment, if we have a network with limited capacity and we do not set any toll price, then people will want to take solo trip where the demand is going to be higher than the capacity, especially on the shortest path, the path with the minimum travel time. If we increase the toll price on edges for this shortest path, then we can either see that people decide to divert to choose a different path, or they may decide to form carpool, and therefore the demand will eventually be smaller than the capacity. Then the road will become congestion-free. So this idea is not new. In fact, it was proposed and studied in this paper of Victory, or even before this, in some other economic and market setting, where that observed the toll price is an invisible hand that balances the demand of trips and supply of the road capacity. So we want to consider this competitive carpooling market proposed by the paper in 2018 by Ostrovsky and Swartz that propose a competitive market framework that addresses the complementarity between carpooling and toll pricing. In particular, this platform represents, for example, a central authority that wants to maximize the social welfare, that is going to set the toll price on edges and incentivize riders to form carpool trips. So here, the riders will have heterogeneous and private preferences of, for example, various parameters about their preferences of what type of trips they want to take. We will go in more detail about the preferences in later slides. But the platform will charge a payment from riders and organize the carpool trip for them, and then clear the market taking the toll price. So here, the toll price is the invisible hand, and the focus of the outcome is market equilibrium that satisfies a set of desirable properties, including stable efficiency, budget balance, and market clearing. So I really like this framework. It's very neat, and it captures this fundamental relationship between autonomous driving, carpooling, and toll pricing. But the paper itself leaves two very important questions open. The first is, because we have these integer constraints, and also because of the network constraint and players' heterogeneous and private preferences, market equilibrium may not exist. And when market equilibrium does not exist, we will have efficiency loss, and we will have instability in the outcome, in the sense that people may not want to follow the trip organized by the platform. So the question of when does the market equilibrium exist, and how can we compute such a large scale, the market equilibrium of such a large scale networked system? I think this is an important question that needs to be answered in order to really build this framework in practice. The second question is, we cannot expect riders to compute equilibrium on their own. So inevitably, such a market will be orchestrated by a centralized platform. But the platform does not have information about the private preferences of these riders. So how can the platform implement the equilibrium while ensuring that riders will truthfully report their preferences? So in this work, we first extend the static carpooling model proposed by the previous paper to extend and consider spatiotemporal carpooling and toll pricing model that really emphasizes the role of network, as well as we allow the travelers to make choice of their departure time, together with the route choice as well as carpool choices. Based on this new and extended model, we answered the two questions that are proposed in the previous slide. In particular, we look into sufficient conditions that guarantee the existence of market equilibrium. We propose a polynomial time algorithm for computing the optimal trip assignment, payment, and toll price in equilibrium. And we also study the strategy proofness to answer the question of how can an equilibrium be implemented through the platform and we particularly look into the case that is not only strategy proof, but also maximizes the rider's utility and minimizes the toll prices that are collected. So solving this trip assignment problem is not easy at all. In particular, this is a large-scale combinatorial optimization problem that we need to decide how to form the coalition, which is an assignment problem of riders to these carpool bundles as well as the trips. And second is, even after we form the carpool groups, how can we route them in the network? That is a dynamic flow problem in a network setting. On the other hand, we need to care about incentives. We want to find payments and tolls that can satisfy the incentive constraints for heterogeneous riders. The first problem of assigning riders to carpool groups is very much related to the literature of combinatorial auction theory that looks into the agent's preferences over indivisible goods when their valuation is not a simple additive, but their valuation is about the bundle of goods that they receive. On the other hand, we find that the dynamic flow aspect of the problem is very much related to the earliest arrival flow literature that looks into the existence and computation of the flow dynamics that ensures the maximum arrival before any time interval of a network. And this problem shows this line of literature demonstrates the existence NP hardness for general setting, as well as pseudo-polynomial algorithm for computing such a earliest arrival flow problem. On the other hand, this is very much related to both the theoretical and empirical study for carpooling and shared mobility problem. And in our results, we developed an approach that particularly combined combinatorial auction theory as well as the earliest arrival flow problem, and to tackle the problem of solving the efficient market equilibrium in this setting. Okay, so let me go to the model, and after the model, I will pause and take questions. So we consider a network where there are edges. Each edge has integer edge capacity, and each edge is associated with a travel time. So a sequence of edge that connects the origin and destination is the set of routes. And we can compute the travel time by summing up the travel time of edges on that route. There is a finite set of travelers who want to take carpool trips at a discrete time interval. So this time interval is their departure time from the origin. And clearly, riders who take the same carpool trip will share a single vehicle and depart at the same time. So the carpool trip is defined by three elements. The Z is the departure time, B is the group of riders, and R is the route. And we want to make sure that feasible trips will ensure two things. One is the rider group size is smaller or equal to the network capacity. And second is that travelers are going to arrive on time, which means they are going to arrive before the last stage of this problem. So we have the decision variable of the system, which is trip organization vector. That indicates if this quantity is 1, then trip that departs at time Z with rider group B and take route R is organized. Otherwise, it is not. And this trip organization vector will determine how the limited edge capacity is going to be shared both spatially as well as temporally. So here are riders with heterogeneous preferences. A rider M's value of participating in this trip has the following components. The first one, alpha M, is the value of arriving at a destination. For example, in a morning time rush hour, one way to set this value is half of the daily salary of this person for commuting to work. And second is the value of time. The value of time can be estimated either through survey or through some inverse estimates with at the system level, which I will go through at the end of the talk. And the second component there is their disutility of arriving late. So remember that riders can choose when they want to depart, and the toll prices is going to be dynamic. So each rider will have a preferred latest arrival time. This person could possibly arrive late. The arrival time is Z plus the time of the route that they take. So then this quantity on the positive component is the delay of the arrival, and each rider M can have a a function of this value, that is their delay cost of arriving time. Lastly, we consider the carpool cost, which has both components. One is a fixed component that does not depend on how long time these riders need to share a single vehicle. This could accommodate, for example, the need of detour and the need of walking to the pickup location. And the second component is the carpool disutility parameter multiplied by the driving time. And this could accommodate the disutility of the need to share a vehicle with someone you do not know for the time TR. Oops. And the social value of the trip is the sum of all riders who participate in this trip and their valuation minus the cost of the trip. We assume the trip cost depends on the driving time as well as the group size. Before I move on, I do want to emphasize that here, our carpool disutility parameters, both the fixed ones as well as the linear slope one, depends on the carpool size and does not depend on exactly who are the passengers who share the same vehicle together. Okay, so we have this. We can write this organizing trip problem, the optimal trip organization problem, by looking at how can we maximize the social welfare of all organized trip, subject to that each rider is only going to be assigned to one trip, as well as the feasibility constraint of the dynamic network flow. I do want to emphasize here that the second component requires you that the capacity constraint of each edge in the network is satisfied for each time interval. And we account for the fact that the trip departs at the time t minus theta RE. Theta RE is the travel time from the origin to reach the tail of edge E when taking the route R. So Z equals to T minus theta RE will ensure this rider group takes the unit capacity at time T of edge E. And when we sum this up, it ensures that the capacity is satisfied at every time step. So this is a very challenging problem with exponential number of variables. What is a market equilibrium here? So here the market equilibrium characterizes the condition for the trip organization, the payment of each rider M, as well as the spatiotemporal toll price for each edge E and each time interval T. It ensures individual rationality in that riders' utilities are going to be non-negative, and their utility is the part welfare they get from participating in the trip minus the payment. Second is that it needs to be budget balanced in the sense that for every trip that can be organized, the total payment needs to cover the toll price. The toll price for every edge at the time of entering that edge, summed together over the entire path that this trip takes, plus the trip cost. And third is that it needs to ensure stability in the sense that riders, no subset of riders, will want to deviate the trip organized by the platform and instead to organize a trip by themselves as well as to pay the toll prices by themselves. The fourth part is market clearing, which considers this desirable outcome that if an edge capacity is not being exhausted for a particular time step, then the toll price of that edge at that time step is going to be 0. We also want to provide a definition of strategy proofness. So travelers are going to follow the assigned trip payment if this is a market equilibrium, and we also want them to truthfully report. The definition of strategy proofness ensures that a market, given an orchestrated market equilibrium, no rider can achieve higher utility by misreporting their preference parameters in their utility function to the trip organizer, which is the platform here. So instead, they're going to truthfully report, and they're going to follow, and they're happy with the organization and payment outcome determined by the platform. Okay, so before I proceed, are there any questions about the overall summary as well as the model setup?
I have a couple of questions,
Yes,
Manxi. So one very basic about the model in the beginning. So you said you have a travel time assigned for each edge.
Mm-hmm.
So this is assuming no congestion, essentially. That until and when you reach capacity, you cannot accept new people on that edge.
Mm-hmm. Yes.
Okay. Then I got it.
So
and the second, oh no, sorry, go ahead.
So I can maybe talk a bit about my thoughts about this assumption. So this basically is like a L-shaped function of the travel time, that if you breach and enter the congestion zone, this is going to increase to infinity. The cost is going to increase to infinity. I thought about considering congestion instead of capacity. I think there's a whole market design framework, as well as I will go to later, that the linear primal and dual will be turned into a convex primal problem, and you can still have the dual. You can still have the market equilibrium defined when you consider congestion instead of capacity. But I think it loses the cleanliness in the computation aspect as well as the equilibrium existence aspect. So still adopted this capacity one.
Okay, thank you. Yeah, no, was just clarification. And
Sure.
Then the second question was typically in these problems when you have when you consider this kind of social cost, which is just a sum of personal costs, you might end up in solutions in which different people are very diverse in their optimality, right? You might have the variance across players, which is big. Like to get the sum to be optimal, maybe one takes 2 hours and one takes 2 minutes. Did I miss something in the last part of your cost function for each player that takes that into account, or does this suffer from what I just described?
So I think so there's a result in later slides that basically shows that market equilibrium corresponds to the socially efficient organization of the trip. And one condition of this market outcome, basically the stability, is the no envy condition. That riders are indeed, the allocation is going to be different, and the payment are also going to be different. So basically you are swapping someone who prefers not to be carpool but does not care about the trip time may take a longer route and take a solo trip. But if you want to arrive early and you don't mind carpool, you will take a carpool trip. And this also depends on their value of time, how much they want their convenience, arriving early, spend less time in vehicle, versus how much they're going to pay to get that desired capacity. But this ensures fairness. I mean, fairness has so many definitions, but this ensures this fairness from the no envy perspective. I think part of the numerical experiment that is still an ongoing effort actually wants to look at, based on different income group, how you want to achieve different types of fairness concept. So for example, a person who has a limited budget to spend on the on paying the toll may actually, for example, a single mom who needs to work for 2 jobs, then this person's time is actually also very valuable, although this is not estimated in a monetary manner. I do believe that the fairness notion is much richer than just this equilibrium definition.
Okay, thank you.
Yeah.
And maybe other people might have questions.
Yeah, I also have a question. So there was a point that you made about some feasibility, right? That there was a capital T involved. I remember the inequality, the constraint. What is that capital T?
Capital T. Oh, yeah, that makes sense. So theoretically, this is just a setting saying that you consider a finite time interval. But I think here you could understand it as, for example, if we want to consider rush hour, then this is like 3 hours. And then we compute the toll price maybe every 5 or 10 minutes. Then T is how many time slots you get. But this T is not the arrival time of each rider. So each rider can have a preferred arrival time much earlier than capital T.
Mm-hmm.
Capital T is just a feasibility set.
So, but the question that I had is the following.
Mm-hmm.
So essentially, this is a feasibility constraint that you impose to say that, okay, so, well, everybody must make it to their destination, right? At some point within this capital T.
They don't
But
have
now,
to.
what do I care that somebody else makes it? So in a sense, this seems to me as imposing a social constraint, right? Like a collective constraint, which will impact individual strategies, right? So I don't really see how this modifies the game in a sense.
So I think it will be more clear later when I present the result, but it does not say that you must arrive at a destination by that time T. It's just that, for example, if you want to go to work, then the latest time that makes sense for you to arrive at the work maybe is before noon. And this capital T is noon time. For anyone who arrive after noon, is considered, for example, you don't get their daily the salary of that day. So then it's the same as them not making the trip. So in equilibrium, it allows people not going to trip. Yeah. So another way to remove this capital T is to say that when your arrival time minus your preferred arrival time is too large, then this function takes the value infinity. So which means that arriving too late is like you'd better just not go.
Yeah. Okay.
And this also accommodates this capital T. Yeah.
Okay. Thank you.
Thank you. Other questions?
Hello, I had a quick question on. You introduced 3 kinds of monetary costs: the CR, then there is a PM, then there is a tau. And I was a bit confused.
So CR is not a monetary cost. This is just a cost of, for example, gas, as well as wear and tear of the vehicle. So this is estimated. And then in the payment part, your sum of the payment for each rider group of this trip should cover the collected toll price plus the cost. So the payment is a total cost splitting mechanism among riders who share a trip.
Okay, so you're paying for maintenance upfront in an end?
Yes, in order to be budget balanced. Otherwise, there is not enough payment to organize the trip.
Okay.
So one simple way to understand this cost is the gas fee.
Okay.
Yeah.
But then, so someone is paying for your gas, or you're taking the gas fee explicitly into account in your payment?
The entire cost of the trip is the cost of using the capacity, which is the toll, plus the gas fee. And then the payment is a way to split it. So if you are a solo driver, you need to pay for all. But if you carpool with someone, you two are going to have a way to share this.
Yes, okay.
Thank you. Any other question? Great, thank you. Thanks for all the questions. Let me go to that slide. Okay, so the results. So the main result has 3: the equilibrium existence, computation, as well as the strategy proofness. So the first result we show is that market equilibrium exists if and only if the primal linear relaxation of the socially optimal trip problem has an optimal integer solution. So we consider this linearly relaxed socially optimal trip organization problem by removing this 0, 1 integer constraints to consider could be fractional trip. And then we can write the dual program. We found that the dual variable actually corresponds to the utility of each rider, as well as the toll price on edge and time interval. And the toll constraint is in fact the stability constraint of the market equilibrium. We also find that the other constraints of the equilibrium definition corresponds to the complementary slackness conditions with respect to the primal and dual constraints. So this result really builds on the fact that the equilibrium condition is equivalent to the conditions in the primal and dual, and using the strong duality, we know that an equilibrium exists if and only if the linear relaxation has an integer solution. So this provides a handy way for us to look into the equilibrium existence problem by turning it into looking at whether or not an integer solution exists in this LP. However, it does not directly provide us a way to compute it, because the primal and dual computation, even without the integer constraints, are very hard due to the large sizes of the carpool group, that our X is a high dimensional vector. Dual variable has a lot of constraints, as well as the network size of edges and roots. So we find examples where equilibrium does not exist. And interestingly, we find two types of example. The first one is this kind of Wheatstone network. And we found that even in a very small scale and simple problem instance, where riders have identical trip value and zero carpool disutility, we find this case where equilibrium does not exist, which is the previous LP relaxation doesn't have an integer solution. The other type of example we found is when the network structure is very simple. It's just a two root parallel network, and also a small problem instance. But we found that when riders have heterogeneous carpool disutility, we also find the case where the equilibrium does not exist. So this motivates us to look into the conditions on both the network topology and the user's preferences to establish our sufficient condition for carpool equilibrium existence. And we find that equilibrium is guaranteed to exist when a network is series parallel, which means such Wheatstone structure is not embedded in the network. And second is that when carpool disutility parameters are homogeneous, non-negative, and non-decreasing in the group size. Question about the statement for this result. Okay, cool.
I have a question.
Please.
How does this relate to congestion games?
It's not a congestion game. It's each edge has a limited capacity. It's a capacitated network, not a congested network. Thank you. Okay, so some practical implications about what are these two conditions mean. So in fact, the series parallel network indicates the important role played by the network topology in guaranteeing the stability as well as social welfare maximization for carpooling market. And similar observation for for series parallel network being better in terms of efficiency for congestion game has also been observed in the previous literature, although in a very different context. Here, this actually indicates that maybe the platform or the system operator will want to set dedicated lanes in order to avoid embedding the network, the Wheatstone network. We also find that this condition can be removed if the system operator is willing to charge toll price based on the path instead of just a linear price on edges. The second is that homogeneous carpool disutility indicates that riders with different levels of carpool disutility should be served separately in different classes of services In particular, riders who have same or similar carpool disutility should belong to the same class and organize carpool trips among themselves, and not with someone whose carpool disutility is very different from them. So the idea of the proof also leads to the computation. So I'm combining the two parts to describe them together. The first step is to compute a dynamic flow problem. We consider the network, So here is the process of computing this dynamic flow. We consider a network where there is no flow at the beginning. And then we iteratively find the shortest path of this network. And for each shortest path, we are going to allocate the maximum possible capacity that saturates this path. Then we take this capacity out from the network to consider this residual network, and we repeat this process of finding the shortest path. So this is a greedy algorithm of iteratively finding the shortest path and also allocate the maximum route capacity for the shortest path that you find. This is a static algorithm, but we are going to turn it into a dynamic flow by considering a temporally repeated flow problem that basically sets for each departure time the capacity that we computed for the static problem, and say that this is the capacity for this route of departuring at time z. Given this way of allocating the edge capacity spatially and temporally to the departure time and route choice according to this dynamic flow, we obtain this key lemma that basically shows that on series parallel network, socially optimal trip organization restricted to only using the capacity assigned by the above temporally repeated flow is also optimal in the original problem. In particular, we find that basically this problem, this LP, is replacing the capacity constraint at the edge level to be at the path level and ensure that the capacity used must only be the capacity assigned by the above algorithm. This is a more restricted optimization problem, but we show that the optimal solution of this one is also the optimal solution of the original problem. So making this restriction does not lead to the efficiency loss. And this result only holds for series parallel. We can come up with examples where this lemma fails to hold on on Wheatstone network. And the second aspect, so remember that we have now allocated the slots of departure time as well as what paths that can be taken. So given these slots, we consider an equivalent economy with indivisible goods. So in this economy, we view the riders as the goods, and we view the slot, each slot that is available in the previous dynamic flow as agent. And rider's utility is basically the good price. So we consider this equivalent Warisian equilibrium for this economy with indivisible good, where basically assigning the riders to each slot of the dynamic flow is equivalent to assigning good to an agent. So here we need to consider a augmented trip value function. So this equivalence is not directly established. We consider an augmented trip value. Why is that? Because the trip bundle size has a capacity constraint. So by augmenting this trip value function, we can turn this function into monotone. So the original trip value function is not necessarily monotone. And second is that given the homogeneous utility parameter as well as the monotonicity property of the augmented trip value function, we can show that this trip value function satisfies Gauss substitutes condition. And based on this result and the result in combinatorial auction theory, we establish that the Warisian equilibrium in the constructed economy would exist, and this is equivalent to the equilibrium trip and utilities given the slots that are organized in the first step. Then combining the two steps, the first step showing that restricting attention to assigning travelers only to these slots is without loss of optimality. And the second step tells you that integer solution exists and also achieve efficiency in this restricted problem. So combining these two steps together, we can claim that this two-step approach indeed compute and demonstrates the existence of a market equilibrium in our setting. And particularly the first step relies on the series parallel network condition, and the second step relies on the homogeneity of the disutility parameters. But riders can still have all the remaining parameters, including arrival time, disutility of arriving late, value of time, etc., to be completely heterogeneous. It's only the carpool disutility that needs to be homogeneous. Okay, so taking the two-step approach, let's compute a market equilibrium. So the first step is basically to find the shortest path, which is to take this route with time cost 2 and allocate the maximum capacity, which is 2. Now we take this route out and we compute the second shortest path, which is time 3 and capacity 1. And third is to take the last route with time cost of 4 and capacity of 1. So we now assign riders to these routes departure time. So I think here we consider departure time to be at most at 4 steps. So the shorter ones will have more number of departuring slots. Given the route as well as the departure time, we assign riders to this process. And this can be done by the Kelso-Crawford algorithm. However, I do want to say that here we need a smart way to iteratively compute the augmented trip value function, which I omit this detail from the slides, but you can find it in my paper, that instead of computing this exponential number of value, we iteratively update this. And this is coupled with the original Kelso-Crawford algorithm that basically iteratively allocate the riders by increasing their utilities and reassignment. And this will lead to an efficient computation of equilibrium. Then we look at the dual problem, and then we use a separation-based LP method for solving the dual problem in order to compute the toll price as well as the payment. So the results I presented in the theorem as well as the algorithm answers the first question of when does market equilibrium exist and how can we compute it when it exists. Now this slide deals with the strategy proofness condition. Is there a market equilibrium where ensures that riders do not have incentive to misreport their preferences? The answer is yes. And in particular, we find that under the two sufficient conditions of series parallel as well as homogeneous carpool disutility, we can find a market equilibrium where riders are going to pay for their social externality, which is the difference of the other riders' welfare with the existence of player I versus traveler I is omitted from the system. And under this payment, riders will truthfully report their preferences over trips, and we can find an equilibrium toll price method to make sure that such a payment is part of the equilibrium. And in this case, the outcome is equivalent to the VCG mechanism. So we ensure that riders are going to truthfully report their preferences over the trip. We find another desired property of this equilibrium is that riders' utilities are actually going to be the highest in comparison to the entire set of market equilibrium. And we also find that the toll prices are going to be the lowest compared to other market equilibria. So I'm going to omit the proof, but basically this proof exploits the lattice structure of the equilibrium utility set. And also it builds on the two-step approach of showing the equilibrium existence. And here what we do is that given the lattice structure and this particular payment vector, we are able to demonstrate the existence of toll price that makes sure this satisfies the primal, dual, and complementary condition, complementary slackness condition for the original optimization problem. Okay, so to have a brief summary of the result, we draw ideas from combinatorial auction theory and quickest network flow problem to look at the sufficient condition for market equilibrium existence, and this demonstrates an efficient algorithm for computing the optimal carpooling and toll pricing. We are also able to compute an equilibrium that is strategy-proof and maximizes riders' utilities. Some of the extensions beyond the assumptions made in the current model is possible. In particular, we can find approximate market equilibrium for riders with heterogeneous carpool disutilities by properly separate these people into different markets and using heuristic or using price and bound algorithms to allocate the network capacity separately for these markets. We can also have an online version of this problem. The extension is actually not very difficult because it also leverages the primal and dual formulation in the original problem. And I believe this results as well as approach forms the connection to the logistics question more broadly, as well as the pricing problem with autonomous shared mobility. Just briefly to talk about a numerical experiment here. We collected a large set of data that uses, depends on the phone GPS, the BART ridership, highway loop detector, and US census data to really estimate people's value of time in the Bay Area based on their income group. And use this way, we are in an ongoing process of redesigning the toll prices that optimizes the social welfare as well as satisfying some equilibrium and fairness constraints. This is mainly the joint effort by two wonderful undergrad students, one from Cornell and one from UC Berkeley. And using this data, we particularly computed a single toll price of the Bay Bridge based on the estimated demand as well as these people's heterogeneous preferences of carpool and value of time for travelers who travel from Oakland to San Francisco. And we consider a 30-minute time slot based on the calibrated data, where each slot has a 5-minute interval. And we separate these riders into two groups. One is the poverty population, which means their income is below $35K per year. And we assume that they're willing to take carpool up to size 10. So this is to reflect that a lot of people in this income group actually relies on public transportation. And we set a spectrum of uniform distribution of their disutility for carpool per person. We also set the toll price. We compute the toll price by proportionally allocated capacity. We find that the toll price for these groups should be $1.5, and they actually form carpool varying from sizes from 3 to 7 in the equilibrium. And for the remaining population, we said that their carpool size is up to 4. This reflects to the current shared mobility, such as Uber and Lyft carpool services. And their carpool disutility, oh, sorry, this is not 0.5, this is $5, is 3 when a carpool size is small, and $5 when a carpool size is 3 or 4 people. And we also compute the toll price, which is $6. And this value is kind of consistent with the current toll price, which is around $8. But using this way of incentivizing carpooling, we are taking the congestion totally away from this Bay Bridge, where right now the Bay Bridge can be super congested during the rush hour. So I think using the framework of carpooling as well as toll pricing, we have the potential to significantly improve the congestion of the network, as well as to improve the social welfare by providing this more flexible way of sharing the road capacity for the low-income population. So thank you. And I'm happy to take questions as many as there are. Thank you.
Thank you, Manxi, for the presentation. let's open the stage for questions. You can either write in the chat or directly raise your hand and I can call you.
Am I able to see the chat? I don't think I can.
You should be able, in case I can read the questions for you.
Let me figure this out.
Yeah, no problem. In case I can read them for you. Okay. Does it, I think Emilio, maybe you want to start? Do you have a question?
No, I don't have a question.
Okay.
Already.
Sorry, I saw you put a video on. And I thought,
No.
I had a question related to your. I mean, I have some questions, but I'll start with one.
Sure.
Like you mentioned, you can build some counterexamples for when your theorem breaks in the case of non-series parallel networks. Do you have an intuition or some? Can you comment a bit more about that?
I see. So this is an example that I found to be very interesting. So because here you actually don't have carpool disutility. So in the combinatorial option sense, this is a very simple problem. So equilibrium should exist, but it doesn't exist here. So the reason is that actually the optimal fractional solution is to have half a trip takes this, half a trip takes this middle link, and half a trip takes the lower link. Theoretically, why does it break? It is because this lemma breaks. So the allocation of capacity to departure time and route is basically an earliest arrival flow problem, because here people want to arrive by a certain time, and you want to, so in order to achieve optimality, you want to allocate as much flow that can arrive before each time step as much as possible. So this corresponds to the earliest arrival flow. And when network is series parallel, earliest arrival flow is this temporally repeated flow. But this does not hold for the Whitson network. So in that case, you have a way to very strangely allocate capacity spatially and temporally, such that you don't have a repetition of what is the capacity that should depart at each time. And actually different time step can have desirably different level of capacity that depart. I know my explanation is probably still too theoretical.
No, but I got okay. some idea.
Sure.
Thank you.
Sure. So this so the proof of this lemma is actually like a construction method of showing that you can reordering the trips departure and route choice in order to improve the optimal solution until you cannot, which is in series parallel. Yeah. Thank you.
Thank you. Thank you very much. Is there any other question? Okay, there is a question from the chat. Hello, Dr. Manxi. Thank you for the talk. I have a question regarding the travel time for edge computation. If we consider congestion, the travel time will change dynamically, and most ride-sharing services jumps on travel. Yeah, okay. This is related to the first question I asked back then.
Yeah. Yeah. So if there's congestion, you still have you actually still have the primal dual, but you don't have this capacity constraint. And instead, your value function will have a latency function. So the value, I'm not showing it here, but value function has this time, and that time is a linear function of the edge load. So you can still have a socially optimal trip organization problem that is a convex program. And then you can write the Lagrangian that basically corresponds to the dual program for this original primal. You can still do the computation following the same methodology that is provided in this talk. But you cannot simply do a capacity allocation. So I believe the results in some sense will hold that series parallel is still important. But how to compute the optimal one, you cannot just solve a linear program. But the insights that equilibrium corresponds to the primal and dual, although they are no longer linear, still hold. I don't know if I fully answered this question.
maybe Vikyat, you can follow. Okay.
Sure.
Thank
Yeah.
you.
But the insight extend, and computation is messier. So
I have a question regarding the numerical study, because it's interesting. You said that you were able to show that you could reduce, based on the study, obviously, but you could reduce congestion in that area. Now, my question is, did you take data for the actual congestion right now, and then you took the same demand and you tried to solve it using your algorithm and you compared?
Yeah. Yes. Okay. So the capacity is basically the maximum observed number of vehicle counts. There's a data set that is 5-minute flow. And we used the maximum one, which is the capacity of the road. And basically right now, not so many people carpool. And the toll price is not very effective in Bay Area. It's not effective at all, to be honest. So this is actually part of an effort of recomputing all the toll price in the Bay Area. But one part that is relevant to this talk is for the carpool. So the reason is that with carpool, you just drastically reduce the number of vehicles on the bridge. So you have a congestion-free setting. Whether or not this can be completely achieved in practice, I don't think it can at the current moment, but with more flexible mobility services, this is possible.
Okay, thank you.
Thanks. So the demand is estimated by the phone GPS as well as the sensor data to rescale how many people want to travel from Oakland to San Francisco during a 30-minute interval.
And you built the network as a series parallel network, like taking how did you do that? Because the road network is
right.
series parallel, right?
So the carpool result I only computed until yesterday, only the Oakland to San Francisco.
Oh, I see.
But we have the entire network calibrated. There's a way to extend the algorithm to multi-commodity network setting. But the algorithm right now takes a long time to run and we haven't finished it. But once that is done, you can actually compute the entire network. Yeah.
Oh, very cool. Whenever you have results, please share with me. I'm super interested in this thing.
Thank you. I think the paper is still under review for equi, so we haven't posted it. We plan to post it after we hear back from the result. Yeah.
Okay, thanks.
Thanks.
I think Edzat has a question.
Sure.
Yes, I have a question on the same slide with regards to the different tolls. So are you proposing of tolling people differently, or is this just a result that the carpooling is different?
Yeah, so you can consider this as the toll price for the bus lane, which right now is also different, is lower than the toll price for private vehicle.
Okay, so it's not that you're necessarily tolling people differently based on their income?
No, not based on their income. Yeah. It's based on the mode of transportation. Yeah.
Okay.
Thank you.
I have another question that
Go ahead.
I think it's interesting that in the formulation of the optimization, you do at the same time the matching and the routing, right? Essentially, you find these minimum routes.
Yes.
Now, there are a lot of people working also on solving simultaneously the rebalancing problem. Have you thought about, are you somehow doing also rebalancing? Or
can you elaborate a bit more what rebalancing means?
Rebalancing, it's essentially a way to put some of the vehicles in places in which the demand might pop up in the future to be more efficient. Because I assume right now, this is not explicit in the formulation, but assume right now you have some initial condition where you assume vehicles are somewhere, and then you are assuming some distances from the vehicles to the people. Maybe those are even fixed right now. I don't know if those are dynamic.
Yeah.
But in reality, this might change dynamically, right?
I see. So Rebalancing is not considered here in the current framework. The current framework considered how the demands spatially and temporally are generated. I would think that to incorporate rebalancing, you might want to formulate a closed network. So you could have like this network is like a chunk of OD, and then you have a set of such network connected together. And you have, instead of this dynamic flow, which is the quickest flow of arriving at particular destination, you have a closed flow that's of circulation. And then you first find the maximum way of circulating this flow. And then you think about how to allocate riders. But this is just a thought. I do not know if this is
interesting.
Sure.
Thank you.
Thank you.
So any final question? Okay, doesn't seem so. Thank you, Manxi. It was a very interesting talk, very cool work. Good luck for the next steps. And I will follow up with the video later today.
Thanks for the invitation. It was great. I really enjoyed the discussion and all the questions raised by the audience. Thank you very much.
Great.
Thanks,
Thank
Emilio.
you, and have a great day ahead.
Yeah, thank you. Have a good day.
Bye-bye.
Bye-bye.